Okay, so we begin lecture 28. And today we are just going to study another feature of complex analysis, which is branch cuts and multi-valued functions. So, consider a contour between these two arcs. I have a theta minimum, I have a theta maximum, and I have an R minimum, and I have an R maximum. So far so good. I mean, we can consider a function fz is equals to square root of z, which is r 1 by 2 e to the power of iota by 2 theta. Z was r e iota theta in its polar form. So r is between r minimum, r maximum on this contour, and theta is also between theta minimum, theta maximum on this contour. So far it seems to be pretty okay. The function seems unique and not multivalued. But consider if I have a contour like this, and I have a theta, I have y, I have x, and so what I do, I start z half equals to r half exp iota theta by 2, and I finish z half equals to r half exponent of iota theta plus 2 pi by 2, which, so I am taking the whole thing when r becomes, or theta goes to theta plus 2 pi, the whole revolution, whole rotation. So that evaluates to r to the power of half e iota theta by 2 e iota pi, and that becomes this guy. So you see there's a trouble here. We are in trouble. R finish had a minus sign and R start was this guy. So the value of the function at the start is not the same as the value of the function at the finish line, even though if you notice, we are evaluating the same point. The same point. We evaluated start, we take the whole rotation, we come back, and this is actually not equals to the same. So basically, even though z start and z finish is the same point, this is not equals to this. So this is an example of a multivalued object, and one idea is to introduce a branch cut. So One idea is to introduce a branch cut. Uh, it's a boundary that one cannot cross. That one cannot cross. So, for example, I can have some sort of a branch cut over here, and I'll define my contours to go avoiding this branch cut. Or more generally, I'll have the branch cuts around the x-axis or the y-axis, and they would be something like this guy, and this would be the branch cut. We are not crossing this line, we are taking the contour around it over here. So the contour cannot cross the branches. So the purpose of the branch cut, the purpose of the branch cut is to get away with the problem of multi-valued functions. So, as an example of the application of branch cut, let us consider the following integral. Now, the minute you see fractional powers, we had this z to the power half, you know that there might be a problem of this multi-valuedness of the function. So first of all, to evaluate such an integral, we need to, as usual, we need to be able to make this into a contour integration and also find a suitable branch cut. So how do we do that? So complexifying this integral would be evaluating it over some sort of a contour, which I'll call gamma, and we need to argue that our choice of contour is such that this contour integration over the complex plane uh, yields the value of the real integral which we are interested in. So by the way, of course, this guy is nothing but, according to our theorem, 2 pi I residue evaluated at z minus a if I choose a suitable contour. So what I'm going to do is to first define the contour to be going arbitrarily close to the x-axis, looping around, and this huge circle, and that essentially over here I'll define my branch cut. And as you know, we have already argued in a few examples earlier that the contribution from this curved gigantic radius, this is 0 as radius goes to infinity. So again, on over this particular contour, this whole contour, I am evaluating this guy, this whole contour. I'm evaluating the function z. I'm evaluating the whole expression, and uh, for this particular branch, if the branch cut is here, for this particular branch I have z half equals to x to the power of half, and for this branch, because it has taken the 2 pi rotation, z half would be nothing but x to the power of half e to the power of iota pi. So now we are all set. This was one of the poles, and I'll call this entire contour as gamma, as I've already indicated over here. So what do we have? We have I closed integral over the closed contour gamma dz over z plus a the whole cube z half, and this is on this contour is equal to the number of the residue of the poles, sum of residue of all the poles enclosed. This has only one pole inside this whole contour, so I'll have this guy as r2 to the power minus a. So now it boils down to first of all finding the residue at z0 equals to minus a. That is my first target, and that is rather easy, right? I put, as usual, I put z as some variable minus a, and expand about this guy. So that is going to, the reason I am doing is that I need to find the residue, which is the coefficient of the -1 power in the Laurent series. So I get fz equals to 1 over psi cube, and that is nothing but, when I evaluate it, this guy, which comes out to be this guy. So the residue is nothing but the coefficient of this term, since this and this would give me the power coefficient in the Laurent series expansion of the power, which is -1. So that gives me -3 iota. This is just algebra. Just try to do it here at your own pace. So what do I have? I have the contour integral dz this is nothing but 3 pi 4a to the power of 5 by 2. Now notice this whole contour integral, since the curved part resides on a gigantic circle of radius goes to infinity, contributes nothing. It all boils down to this integral and this integral. And why is this particular choice of integral useful? Well, this is integral 0 to x, 0 to infinity over the real line, and this is integral from infinity to 0 over the real line with these definitions. So indeed I'll have this whole integral over the, I'll just label the integral by dot dot. This is nothing but dz ab. So I'll just call this a, b, and this is c and d, these points, plus the same integral cd, which gives me evaluating this side, since z is, I can express z in terms of x. And now x changes its definition to be, remember this was my branch cut, so the whole rotation, this guy over here is x e to the power of, so this guy is nothing but x e to the power of 2 pi iota. So that gives me x half e to the power of iota pi, and that is equal to the value of the contour integral I evaluated. So now it's good. I have the integral which I needed to evaluate, and well, I just solve it. I just solve it for these guys. This is 1, this comes out. So ultimately, when the algebra clears up, this is and so ultimately, when I finally evaluate the integral, that would come out to be, so this integral will come out to be, when the smoke resolves, 8a 5 by 2. So this is the way I first converted the integral into a complex integral. I made a judicious choice of the contour with the branch cut, and then I argued that the entire contribution of the whole contour integration was from these branches, which carried different values of the complex number z, since this is a multi-valued thing and I have to respect the rotation, but I keep in mind that the function doesn't go multi-valued because I have to respect this branch, the boundary. So by the judicious choice of the branch cut, I am able to evaluate this integral to be this. So this is nothing but, what did I set to? This guy. So that was an example of one of the problems involving a branch cut. Now you had exactly a very similar problem in your problem set. So from your problem set. So the question was, using a suitable cut plane, prove that if alpha is an element of R and then so that was required to be shown, and ultimately it's the same thing. It's a similar question. The moment you see alpha less than 1, you automatically know that this function will run into some issue of multi-valued problems. So I again choose a similar sort of a contour, take this radius going to infinity, and this is my branch cut. I again define A, B, C, D the same way. And well, what is this integral first of all? So when I complexify this integral, this is nothing but dz z minus alpha over 1 plus z, and that, according to our standard Cauchy formula, that would boil down to 2 pi iota minus 1 to the power of alpha, or 2 pi iota e minus pi iota pi alpha. And I have to argue that this contour integral is, so mind you, I could have used the residue theorem, or when the residue, sorry, I could have used the residue theorem, which is the most general case, or I could have used the Cauchy's integral formula. It's the same thing. So I argue that this contour integral over here, over gamma, this is equivalent to 2 integrals over the real axis with a different definition of x, because I've done a 2 pi rotation. So this is the CD integral, this is the AB integral. This is page number 8. And well, then that is nothing but I evaluate both these integrals from 0 to minus infinity. And that would give me, when the smoke clears, this is equivalent to this integral which I have already solved. And when the smoke clears, you will get this guy, the integral as which is nothing but pi cosecant pi alpha. So that was the concept of avoiding a multi-valued complex function, introducing a branch cut, and application of these things, branch cut, to contour integration. Okay, thank you.